Well, hello everybody. This is the first lecture of the 6th week, so we're approaching halfway in our lecture series this term. In this lecture I'm going to be looking at the Poisson family of distributions. So last time I was talking about the Bernoulli trial leading to a set of 3 distributions from the binomial family, and they counted things like the number of successes in n trials, the number of trials until the first success or the next success, and the number of trials until the kth success. Now we're going to switch to another set of 3 distributions that also derive from this idea of a set of Bernoulli trials. And the Bernoulli trials, as you remember, have 2 possible outcomes. We generally call them success failure, but it can be 0, 1, black, white, yes, no, true, false, whatever. Just as long as there are only 2 of them. And the other things about those trials is they have to be independent from one another, so the occurrence of success in one trial doesn't affect the probability of a success in a different trial, and the probability of success remains constant from trial to trial. So today, this lecture we're going to talk about the Poisson family of distributions, and this is going to be a bit of a longer lecture. I probably made a mistake. I put all 3 of them into one set of notes. I probably should have split them up, but maybe I'll put some timestamps in so you can see where each of the distributions start. Okay, so in the Poisson family distributions, what we do is instead of a sequence of discrete trials, we now let every instant in time become a Bernoulli trial. And that means that at any time interval you've got an infinite number of trials, but it also means that successes, or this is commonly arrival processes, successes or arrivals can occur at any instant in time now. Okay, so basically now these, as I said, the successes can occur at any instant in time. This could also be over space. It doesn't have to be in time, but most of our models are interested in time processes, so we'll concentrate on time. But I think there will be a few questions that you'll see in the example problems or the assignment where the Poisson process is occurring over space. Okay, so the problem we face now is that every single time interval contains an infinite number of trials. In other words, the number of trials is going to infinity. If you recall, the expected number of successes or arrivals in n trials is n times p. Now, if n goes to infinity, then infinity times p goes to infinity unless the p's go to 0. So, in other words, if you have a non-zero probability of success, then this particular model will always lead to an infinite number of successes in any time interval, and that is not very useful to us. So basically, we have to have that the probability of success on any instant goes to 0. Actually, it goes to being equal to the or proportional to the size of the instant. Like I said, we don't see in practice an infinite number of successes at any time interval. So p goes to 0. In other words, we can no longer use p itself to characterize this particular process. The solution is we replace p with lambda, where lambda is mean rate of success now, or mean rate of arrival. It's the number of occurrences per unit time. Remember that this is a rate, so it's per unit time. And this idea leads to 3 more distributions. I put on the left-hand side the distributions we've already seen: binomial, geometric, and negative binomial. Then we say, okay, every instant is becoming a trial, and we get the analog to the binomial becomes the Poisson distribution. We're going to call it n sub t, and this is going to be the number of arrivals in time interval t. The next 2 on the right-hand side are the first 2 common continuous distributions that we look at. The first 4 here, binomial, geometric, negative binomial, these are counting number of trials, and so they're discrete. Poisson is still counting number of trials, but now it's number of trials in a time interval rather than number of successes. Sorry, I should be saying number of successes rather than number of trials. On this side, it's number of trials till the first success, or the number of successes in n trials, and so on and so forth. Poisson is still number of successes in time interval t, so it is also discrete. Exponential is going to be, now time is measured continuously, is the time to the first success or to the next success, and gamma is going to be the time to the kth success. Okay, and those last two, as I said, are continuous. All of these distributions, all 6 of them, are based on this idea of that simple random variable Bernoulli trial. Let's first of all talk about the Poisson distribution, and let nt be the number of successes or arrivals in time interval t. This is, as I mentioned, the continuous time analog to n sub n. Okay, so n sub n is measuring time in number of trials, whereas n sub t is measuring time in actual time. And as I mentioned, arrivals or successes can now occur at any instant in time. So I usually draw the Poisson process along a time interval, showing a picture of something like this. I draw the time axis, and then when arrivals occur, I draw a little x. And so a typical Poisson process looks something like this. You get little x's whenever people arrive at the bank, or arrive at your website, or whatever, or arrive at an intersection. And these arrivals occur at a mean rate, which we call lambda. So this uppercase here gave an nt, so the number of arrivals in time interval t, here's t, was 1, 2, 3, 4, 5, 6. Okay, the 7th arrival occurred after time interval t. And the next realization of this process, the arrivals are going to be at different times, and this particular one gave me nt equals 4. So I had 1, 2, 3, 4 occurring within time interval t, and the 5th one occurs after time interval t. Okay, so the number of arrivals in some time interval, we know that's random. Every realization will be different, or could be different. So we need to figure out what the distribution is. If we look at the distribution of the binomial, we saw that probably that the number of successes in n trials is equal to k, was n choose k, p to the k, q to the n minus k. And now what we're going to do is we're going to take n going to infinity, and p equal to the time interval divided by n. And as n goes to infinity, of course, this goes to 0. So p itself we don't ever use after this, but if we look at the limit of this expression, as n goes to infinity and p goes to t equal to t over n goes to 0, then it turns out that the resulting distribution, although it looks entirely different, is derived from this distribution in the limit. So we get probably nt of the k is lambda t to the k over k factorial e to the minus lambda t. Okay? So we see here the rate, the time interval, and the number of successes that we're talking about. So that's the distribution, and now we can talk about the main characteristics of this distribution. The first would be, what is the expected number of successes in time t? Strictly speaking, that's the sum of all possible numbers of successes, which goes from 0. Oh, I should have put in this previous expression what the possible values of k are. And they are for k equals, well, this is the number of successes in time t, or arrivals, and we could have 0. So the lowest value of k is 0. We could have 1, we can have 2, and the upper value, there's no limit. There's an infinite number of trials in any time interval t, so this could conceivably go to infinity. What that means is that the main characteristics down here, the expected value of nt is the sum of all possible values of k. That goes from 0 to infinity, of k times their probability of occurrence, probability that nt equals k. And that gives me k lambda t to the k over k factorial e to the minus lambda t. And that's an infinite sum as well, so that's a difficult thing to solve. But intuitively, we can think about this as follows. Suppose I tell you that on average 5 customers arrive at a bank per hour. How many do we expect in the next 3 hours? Well, that's pretty obvious, right? 3 times 5 is 15. So basically, the expected value of n3, which is the 3 hours, is 3 times 5, 15 arrivals in the next 3 hours. And we get that by multiplying the number of hours times the rate. Actually, I write it the other way around here, but in general, the expected value of nt is the rate, lambda, times t, so lambda t. Okay, and that makes sense. And in fact, this particular summation up here will turn into this result at the end. Let's see, I skipped the variance. Let me just write that in. It's the same sort of idea. Oops, that's the wrong thing. Variance of nt is also equal to lambda t. Let me just check that with, you can look at it, it's listed in the summary pages, so that's given to you, and you can check to see if I've got that right. I'll check as well, and if it isn't, I'll put a correction in this video. Okay, so let's take a look at an example. And I'm going to call this example 4.6, and let's suppose that paper called the Reliability-Based Service Life Assessment of Aging Concrete Structures suggests that a Poisson process can be used to represent the occurrence of extreme loads over time. So basically we're saying, okay, extreme loads occur randomly in time, and they occur according to a Poisson process. That means that they occur like we see in this picture up here. So here's an extreme load, here's another extreme load, here's another, and so on and so forth as a function of time. And the number of those occurring at any time interval is given by the Poisson distribution that we just covered. Suppose the mean time between occurrences of extreme loads is half a year. Well, okay, so that's the mean time between occurrences, and we're told up here, well, that's expected, well, okay, so mean time between occurrences is half a year. What we're interested in is the rate of occurrences. So if the mean time between occurrences is half a year, then we expect how many per year? Well, it's going to be 2 per year, right? Yes, okay, that's what we get here. So we expect 2 occurrences per year, so lambda is 2 per year. In fact, this gives us a result here that the expected number in 1 year is 1 over lambda. Oh, it's lambda times 1. Yes, okay. That's 2, of course. Okay. Okay, so we've got lambda. What's the first question? How many extreme loads can be expected to occur during a 2-year period? Well, we've got t is now 2, and we know what lambda is, so we got expected value of n2 is lambda t, which is 2 times 2, which is 4. So in 2 years we expect 4 occurrences per year. And again, if we know that the occurrences are on average a half a year apart, then in 2 years we expect 4 to occur. That makes sense. Part B is, what is the probability that more than 5 extreme loads occur in a 2-year period? So that basically we're looking at the 2-year period is t is 2, so the number of occurrences in 2 years is to be, what's the probability that it's more than 5? Well, the problem with this one is that it's if it's more than 5, then it's either 6, or it's 7, or it's 8, or it's 9, or it's ... and that goes off to infinity. Well, the first thing we want to ask at least is, are these things disjoint? Well, clearly if n2 is 6, it can also be equal to 7, so these are disjoint. So no problem there. We can turn the unions into plus signs, but I don't want to be adding up forever. So much better way of doing this is to write it as 1 minus. So the probability that n2 is greater than 5 is 1 minus the probability that it's less than or equal to 5. And now at least I only have, what's that, 6 terms. So 1 minus the probability that it's 0, probability that minus the probability that it's 1, minus the probability that it's 2, up to the minus the probability that it's 5. Now I just go back to my distribution for the exponential, which was, for the Poisson, which is given here, and substitute this in for each of these terms. And we get probably that n2 is 0 is lambda t to the 0 over 0 factorial e to the minus lambda t. Probably that n2 is equal to 1 is lambda t to the 1 over 1 factorial e to the minus lambda t, and so on and so forth up to probably that n2 is equal to 5. The e to the minus lambda t is common. I can bring that out front, so I got that there. And then I just have inside a sum of things that involve lambda t. In our particular case, lambda t is 2 times 2, so they're all 4s. So we get 1 minus e to the minus lambda 4, e to the minus 4, times 1 plus 4 squared over 2 factorial, and so on and so forth. And altogether I get, the result is 0.215. Now we get to the second of the group of Poisson distributions, and this is now under continuous distributions, because this one is now measuring the time to the next occurrence of arrival or a success, and time is now continuous. Okay, so every instant is a trial, and that distribution is called an exponential distribution. So this is the continuous time analog of the geometric distribution, and is our first common continuous distribution. Continuous distribution, okay. So let's define T1 as the time until the first or next success or arrival. And of course then T1 is random, and we have to take a look at what its distribution is. Let's as usual consider a specific example and see if we can use that to derive the distribution of T1. Let's take a look at the probability that T1 is greater than T. Now remember, T1 is the time to the next success or arrival. So if T1 is greater than T, it means my X is beyond the position T. Okay? In other words, between here and here, I have no arrivals. Okay, so NT is equal to 0. That means the probability that T1 is greater than T is also equal to the probability that NT is equal to 0, which I'm writing here. And I know what this is. That comes from the Poisson distribution. It's lambda t to the 0 over 0 factorial, which is 1, e to the minus lambda t. So it means probably that T1 is greater than T is just e to the minus lambda t. Now this is a greater than. If I turn it to a less than, then I get capital F of T1. So the cumulative distribution function of T1 is the probability that T1 is less than or equal to T is going to be 1 minus this thing, which is 1 minus e to the minus lambda t. And this is for any t greater than or equal to 0. If I actually want the probability density function, I can differentiate this, and I get little f of t1 is equal to lambda e to the minus lambda t. Again, for t greater than or equal to 0. And I can plot this. I know that lambda e to the minus lambda t is an exponentially decaying function. When t is 0, this function is at lambda on the vertical axis. And the mean of this, as it turns out, is 1 over lambda. And we'll see that in a minute. But it's the balance points of this distribution. Because we have this long tail out to the right, the balance point is pulled out to the right. Okay, so this is what this distribution looks like. Although it seems to suggest that we have more T1s close in, what it does actually mean that, but it means that basically if we look at our plot of what happens, is that we tend to see groups of occurrences and then every now and then a long space. So it looks like this is a sort of clustered process, but in fact what's happening is that every realization in any case, every trial has the same probability of occurrence, same probability of a success. So that's what the distribution ends up looking like when the probability of success remains constant with time. Okay, main characteristics, the expected value of T1, this is the expected time between occurrences, is the summation of all possible values of t, which is 0 to infinity, times their probability of occurrence, which is little f of t times dt. This is, we have to integrate this by parts, but once we finish doing that, it'll turn out to be the expected time between occurrences is just 1 over the rate. We kind of saw this earlier. We were told the expected time between occurrences in that previous example was half a year. And that meant that on average our rate of occurrences is 2 per year. Well, that's just 1 over half. In other words, expected time between occurrences is 1 over the rate, or the rate is 1 over expected time between occurrences. Then we expect the time, okay, so this is just a repeat of that. Variance turns out to be, we plug it into this, we have a t squared here, and we end up with variance of T1 is 1 over lambda squared, which means the standard deviation of T1 is 1 over lambda, so that the standard deviation of this random variable, exponentially distributed random variable, is equal to the mean. And that's one of the features of an exponential distribution, that the mean and standard deviation are the same, so the coefficient of variation is 1. Well, this exponential distribution, because it's derived from the idea of a sequence of independent Bernoulli trials, has a memoryless property. In other words, all the trials don't remember anything about the past. In fact, they don't remember anything about the future either, because all of the trials are independent. But it's sort of illustrated in this example about this business of forgetting the past. Suppose that we turn a light bulb on and observe that it lasts for t hours. Okay, so if we turn on a light bulb, it lasts for t hours. What is the probability that it lasts for a further s hours? And let's assume that the time to failure of the light bulb is exponentially distributed. Okay, so what's the expression of this probability problem? we're told that we've observed it to last for t hours. So we know we're given that t1, time to failure, is at least equal to t hours. Okay? And we're now asking what is the probability that it lasts for a further s hours. So the probability that it's that t1 is equal to is greater than t plus s. Okay? This should really be that it lasts for at least a further s hours. So t1 is greater than t plus s. Well, our fundamental definition of a conditional distribution is the probability of the intersection between these things divided by the probability of the given part of it. So I write it this way. Probability t1 is greater than t plus s intersected with t1 greater than t divided by the probability that t1 is greater than t. Okay, so if I look at the top, we can see that the right-hand one, the left-hand one, probably that t is greater than t plus s, is a subset of the probability of the event that t is greater than t. Okay, so all of the values in this region here are included in this region here. So the intersection between the two is just this part. Okay, so this boils down to the probability that t1 is greater than t plus s divided by the probability that t1 is greater than t. Now I go back to my probability definition for this this greater than part, and I have to look back up where we derived that. Here, probability that t1 is greater than t was e to the minus lambda t. So when t is equal to t plus s, I get e to the minus lambda times t plus s, and when t is just t, I get e to the minus lambda t, and the lambda t's cancel out here, and I've got e to the minus lambda s, and this, of course, is just equal to the original probability that t1 is greater than s. Okay. In other words, it didn't matter that it lasted for t hours. The probability that it's going to last another s hours is exactly the same as when we first turned it on. Okay, and this is again an illustration of the fact that every instant has the same probability of failure, and all of the trials are independent. So the fact that it lasted t hours doesn't make any difference to the next trial. It doesn't remember that at all. The probability of it failing is exactly the same as it was from the start. Okay, so yes, as I mentioned, failure problem remains constant with time. So another example we could look at, let's suppose an amplifier clips a signal when it exceeds a certain high threshold. An engineer observing this signal produced by a heavy metal rock band determines that excursions follow a Poisson distribution. This is perhaps not a very realistic research endeavor, but presumably this engineer has decided to model the signal, the excursion process of a heavy metal rock band, and has decided that this follows a Poisson distribution. So basically we got a picture that looks something like this. Here's your volume as a function of time from the heavy metal rock band, and every now and then it goes above this clipping threshold. So that sounds horrible. Basically, okay, we're saying, okay, nt is the number of excursions in the time interval 0 to t, and lambda we're given as 0.5 as the mean number of excursions per second. That's a lot, isn't it? Oh, that's 0.5, that's half of an excursion per second, so we expect to see an excursion every 2 seconds. That probably makes the sound pretty bad. Let's suppose that if an excursion is observed at time t0, then what is the probability that the next excursion occurs after t0 plus 2 seconds and before t0 plus 3 seconds? And then perhaps list possible problems with this model. Okay, so let's suppose we observe that we had an excursion at time t0. We don't really care when t0 is. If this is a Poisson process, every trial that comes after that is independent of that particular instant in time, t0. So we can set that to any number we want, but it's easiest to set it to equal to 0. So we'll assume that we start observing at time 0. We had a threshold excursion at that instant in time, but if this is truly a Poisson process, the next trial, the next instant, has nothing to do with that first one. So it doesn't really matter what happened on that first instant. It's just that we start looking at that instant. Okay, so basically what we're looking for here is the probability that the next excursion will occur between time 2 seconds and 3 seconds if we take t0 equal to 0. I've written it out here as t naught plus 2 to t naught plus 3, being the integral from t naught plus 2 to t naught plus 3. In fact, this is, again, if I draw this curve like this, then I'm assuming that t naught is actually at 0. So this is actually from 2 to 3. And I've written that down here. We're going to actually do the integral from 2 to 3. Then we take t naught as 0, and then we actually want to compute the probability that 2 is less than or equal to t1 is less than or equal to 3. So t1 lies between 2 and 3. Is then the integral from 2 to 3 of the little f, so the probability density function times dt, which is lambda e to the minus lambda t dt. And this is also, we can do this in terms of the cumulative distribution function. I did something wrong here. This should be a 2 here. 2. Okay. So cumulative distribution function, and we know that that area between these 2 points is just the cumulative distribution function up to 3 minus the 1 up to 2, and that gives us the area in between. If we look at our summary pages, the cumulative distribution function for the exponential is 1 minus e to the minus lambda t, and t in this case is 3. That's ft of 3. And then the next one is ft of 2, so 1 minus e to the minus lambda t, or t is 2 now. The ones disappear, we get e to the minus 2 lambda minus e to the minus 3 lambda. We know lambda is 0.5, so I just plugged in the numbers and I get 0.15. Well, what are the possible problems with this model? The excursions are not exactly independent, which is to say the occurrence of one to the occurrence of the next may be independent, but once we've gone above, I get a whole pile of instances that are all successes. So these instances, shortly after that occurrence of a excursion, they are very dependent on the excursion, the occurrence of an excursion. So the best way to model this, to think about this, is to forget about what's happening immediately after an excursion takes place, but just look at the upcrossings. So this is one arrival, this is another arrival, this is another arrival, and this is another arrival. And it turns out that if that threshold is high enough, that this will generally approach a Poisson process. These are upcrossing approach problem. Concentrate on upcrossings only. Okay, so this one is the analog to the geometric. It's measuring the time to the next arrival or occurrence. The third distribution that we looked at in the binomial family was the negative binomial, and that was measuring the number of trials till the kth success. When time became continuous, so every instant became a trial, that we're now measuring time to the kth arrival. So we're going to define tk to be time to the kth arrival. Now this is continuous because time is continuous. And as I mentioned, this is now the analog of the negative binomial distribution. And again, it's a distribution, a generalization of the exponential distribution. If I let k equal to 1, then I'm going to get back to the exponential distribution that we're talking about up here. Well, the distribution for this one is, again, found by taking a look at a particular example. Let's look at the probability that T3 is greater than T. Well, if T3 is greater than T, all we know is that the third arrival is sometime after the time T. So we have some possibilities here. One is that all 3 arrivals occur after T. But another possibility is we have 1 arrival in here and then 2 arrivals after time T. And another possibility is we have 2 arrivals in here and the third after T. There are no other possibilities. If we have all 3 inside, then T3 is less than T. Okay, so if we want T3 to be bigger than T, these are the only 3 possibilities. So the probability of this happening is the probability that we get this outcome, or we get this outcome, or we get this outcome, and that's a union. And then the question is, are these 3 things disjoint? Well, if we had none occur in time T, then we could not have had 1 occur in time T. And we couldn't have had 2 occur in time T. So basically, yes, these things are disjoint. and that means I can replace these unions with plus signs. So we get, so this thing here is probably that nt equals 0, or nt equals 1, or nt equals 2, sorry. And I'm getting that by looking at what these things mean. If all the three of these things are outside of t, then that means nt is 0 here. If we had 1 in here, then nt is 1. If we had 2, then nt is 2. And as I said, these are disjoint, so that's probably that nt equals 0, plus probably nt equals 1, plus the probability that nt is equal to 2. And I have the expressions for that coming from the Poisson distribution. I just substitute in the formula for these probabilities. So probably nt equals 0 is lambda t to the 0 over 0 factorial, which is 1, e to the minus lambda t. Probably nt equals 1 is lambda t to the 1 over 1 factorial e to the minus lambda t, and similarly for nt equals 2. And so I can write this, probably the t3 is greater than t, is I can factor out the e to the minus lambda t, and I get 1 plus lambda t over 1 plus lambda t squared over 2 factorial. Or I can write this as a sum. E to the minus lambda t, the sum of j equals 0 to 2 of lambda t to the j over j factorial. Now this is greater than t, so if I want the cumulative distribution function, which is generally what we look at for the gamma distribution, it's just going to be 1 minus this. Cumulative distribution function, capital F, is defined as the probability that t3 is less than or equal to t, which is going to be 1 minus this thing. So 1 minus e to the minus lambda t, j equals 0 to 2, lambda t to the j over j factorial. And if you take a look in your summary pages, this is the cumulative distribution function that's given to you for the gamma distribution, and here I've just written it out again. Oh no, this is the, now for, in general, for any k, we're going to get 1 minus e to the minus lambda t, and this sum goes from 0 to k minus 1. So it depends on how many, which arrival you're looking at. Okay, main characteristics. Just as we had for the negative binomial, we can write the time to the third arrival as the time to the first arrival, plus the intervening time to the second arrival, plus the intervening time to the third arrival. And all of those 3 times, they're exponentially distributed. So the gamma distribution that I get here is actually a sum of exponential distributions. And these exponentials are all independent. Okay, so the picture here is this. If t3 is the time to the third arrival, and then the time to the first one is this t1. Once that has occurred, the time to the second one I'm going to call t1 subscript 2. And once that has occurred, the time to the third arrival is t1 subscript 3. So t3 is this, plus this, plus this. And these are all exponentially distributed and independent. So once we have made that observation that t3 can be written as the sum of these 3 independent exponentially distributed random variables, then the mean of t3 is just the expected value of that sum. Excuse me. And the expectation of a sum is, of course, sum of the expectations. So to break it up at the plus signs, this is the expected value of a t1, t11, plus the expected value of another t1, t12, plus the expected value of another t1, that's t13. They're all independent, and they all have the same expected value, which is 1 over lambda. So in the end, I get expected value of t3 is 3 over lambda. And in general, expected value of tk is just k over lambda. For the variance of tk, we use the same sort of idea. The variance is going to be the variance of this sum, and if these terms are independent, then the variance of that sum is just the sum of the variances that we have here. Because these every trial is independent, the times between occurrences are also independent. So these things are independent. So this variance of tk becomes the sum of k variances. And each of those has variance 1 over lambda squared, so variance of tk is k over lambda squared. Okay, so referring back to a previous example, that's the one about the excursions. The question is, what is the probability that the third excursion will occur within 5 seconds of the start, which we'll assume is within 5 seconds of time 0. And we're only going to look at these upcrossings, so we're not going to worry about the fact that this is a bit of an approximation once an upcrossing has taken place. Okay, so we're interested in the third excursion, so we're interested in T3. So that's the time to the third excursion. I've got one here, another one here, another one here, so that T3 is where we had that third X. So K is equal to 3. And we're looking for the probability that T3 is within 5 seconds, less than or equal to 5. And so this is the cumulative distribution function up to 5. And so if I look at my summary pages, that tells me the CDF, or capital F, for T3 is 1 minus e to the minus lambda 2t, and the sum here goes from 0 to 3 minus 1, which is 2, and lambda t to the j over j factorial. And we're told t is 5, so we know what t is, and we also know lambda is 0.5, so we know what lambda is, and so we know everything on the right-hand side, we just have to plug in the numbers. So lambda t is 2.5, so we got 1 minus e to the minus 2.5 times 1 plus 2.5 plus 2.5 squared over 2 factorial. And that gives me 0.4562. So far we've just talked about the cumulative distribution function for the gamma distribution, and usually that's all I'm concerned about, because we use that to find probabilities. But if we are interested in the probability density function, we just have to differentiate the cumulative distribution function. In a more general sense, the PDF then is this function lambda over gamma of k. This gamma is a so-called gamma function. We are always dealing with k being integers, so I should really have written this as lambda over k minus 1 factorial, lambda t to the k minus 1, e to the minus lambda t. Anyhow, what does this look like? It basically looks something like this. We know, I should have put this in here, if this is k is 1, let me just draw this in here. We get this. So this is k equals 1. Because if k is 1, this is the time to the first arrival or excursion, and this is exponential. So this looks has an exponentially decaying curve. But as soon as we have 2 time to the second or third or fourth, as soon as we have time to the second, the probability of having 2 at time 0 vanishes, becomes vanishingly small. So this distribution starts off from 0 now. I've lost my here. Starts off at 0, climbs up, and then decays. The other thing that we know is that as we are looking at the time to more and more occurrences, the average is moving off to the right, right? The mean expected, have we done that? Yeah, where is the expected value? The expected value of time to the kth arrival is k over lambda. So as k gets bigger, the expected value gets bigger. Of course, that makes sense. We expect to wait longer to see the 10th arrival than to see the second. So what happens is that this distribution gradually moves off towards the right as k gets bigger and bigger. We'll see something later called the central limit theorem, and it says that sums of random variables tend to a normal distribution. We haven't actually covered the normal distribution, but I'm sure that you all are familiar with the normal distribution. It's the bell-shaped curve. This tk, where is it here, is a sum of random variables. So tk is t11 plus t12 up to t1k, and as the number of these terms gets bigger, the distribution becomes more and more normally distributed, more and more like a normal distribution. And we can see that here. When k is 2, it doesn't, I mean, it looks a little bit like a normal, but it's skewed to the right. Whereas when k is 10, it's now looking pretty much like a symmetric bell-shaped curve. Okay, so summary here is that the second set of distributions coming from the idea of a sequence of independent Bernoulli trials occurs when we let every instant in time or space become a trial. That gives us these 3 distributions. Poisson is the number of successes in time interval t, and this is still discrete. But the next 2, exponential and gamma, exponential is the analog to the geometric, but time is now continuous. So in the geometric we're measuring time in number of trials, now we're actually measuring time. And so T1 is a continuous random variable, and it is the time to the next arrival in the Poisson process. and gamma is the analog to the negative binomial, except negative binomial was counting time and number of trials. Now we're counting time explicitly, and so tk is the real time until the kth arrival. Okay, and that's the Poisson family. So now we've got these 6 distributions. As I mentioned, this idea of Bernoulli trials can also lead to another set of very powerful models, and those are Markov chains and queuing processes. We're not going to talk about those in this class, but you will possibly see them in some of your later classes or in real life, particularly if you go into things like transportation engineering, financial engineering, lots of problems in industrial engineering deal with Markov and queuing processes. I guess that's it for this is week number 6, first lecture. And next lecture I'm going to carry on with other continuous common distributions. Okay, bye-bye.